All right, let's jump right in. Today, we're going to break down a really complex topic, autoimmune visual loss. The goal here isn't just to recite a textbook, but to give you a solid clinical framework you can actually use when you're evaluating a patient. So let's start with a classic case. Picture this. A young adult walks in with painful progressive vision loss in one eye. This scenario is perfect because it's going to walk us right through all the core concepts, from the basic anatomy all the way to the critical diagnoses you absolutely need to have on your radar. But, before we can figure out what's going wrong, we've got to have a solid handle on what right looks like. So first, we need to appreciate the amazing hardware of our visual system and the clever defenses the body uses to protect it. Okay, so this image gives us a fantastic roadmap of that visual journey. I want you to think of it like a hardwired cable, a direct line running from the retina through the optic nerve all the way to the visual cortex in the back of the brain. And what's crucial is that any break or disruption along this cable is going to cause a very specific, predictable blind spot in your vision. Now, let's zoom in on the retina itself. What's so cool about this image is how it shows us the different layers. You've got the photoreceptors up top, they're the ones actually catching the light. And then you have the ganglion cells down at the bottom, and their long tails, or axons, bundle together to become the optic nerve. The key takeaway? Each one of these cell layers can be a specific target in an autoimmune attack.
So that begs the question, right? Why isn't our own immune system just constantly attacking this super delicate system? Well, the answer is a concept called immune privilege. Basically, the eye and the brain are walled off, intentionally kept separate from the rest of the body's inflammatory chaos to protect all those sensitive neural circuits.
And this is how the body does it. This diagram shows the blood-brain barrier and its counterpart in the eye, the blood-retina barrier. Think of them as high-security walls with very strict gatekeepers. They stop rogue inflammatory cells and antibodies from just waltzing into the central nervous system.
Okay, so we've got the defenses down. Now, let's get to the interesting part. What happens when those defenses get breached? This is where we start building our list of suspects, our differential diagnosis.
So yeah, what does happen when the immune system gets past these barriers and starts targeting the visual pathway? This is the central question we have to answer when a patient like the one we started with shows up. The answer to this question is what forms the core of our differential.
And if we're playing the odds, for a young adult with painful, one-sided vision loss, the most likely culprit is optic neuritis, specifically the kind associated with multiple sclerosis, or MS. In fact, it's often the very first sign that leads to an MS diagnosis.
This map is really fascinating. It shows that the chances of getting MS aren't the same everywhere in the world. It's way more common the further you get from the equator. This crazy geographic pattern is a huge clue that MS is likely caused by a complex dance between our genes and something in the environment.
But, and this is probably the most important point I'm going to make, not all optic neuritis is MS. I cannot stress that enough. Getting this wrong and mistaking an MS mimic for actual MS can have absolutely devastating consequences for a patient's vision.
All right, this table is your go-to cheat sheet for telling these conditions apart. Just look at the pattern. MS optic neuritis, usually moderate, and the patient almost always gets better. NMO, it's the opposite, often severe, and the recovery can be poor. And check out the MRI findings. MS causes a short little lesion in the optic nerve. NMO, on the other hand, causes these long, angry-looking lesions that can stretch all the way back to the chiasm. So why are they so different? Well, it's because NMO is a totally different disease at the microscopic level. It's not primarily an attack on myelin like an MS. No. NMO is what we call an astrocytopathy. The immune system is going after these things called aquaporin 4 water channels, which are on support cells called astrocytes. And when it attacks, it brings the full force of the complement system, leading to just massive destruction.
And just to make things more interesting, there's a third major player you need to know about, MOG antibody disease, or MOGAD. In this case, the immune system is targeting something called myelin oligodendrocyte glycoprotein. What does this look like in the clinic? Often, it's a severe, recurrent optic neuritis that seems to get better with steroids, but then comes roaring back the second you start to wean them off. Okay, let's look at a real-world case of MOGAD to see what I mean. These MRIs tell the story perfectly. On the left, you can see that bright white enhancement in the left optic nerve. That's the first attack. Then, a year later, on the right, the left eye has cooled down, but boom, there's a brand new attack in the right optic nerve. That is the classic relapsing pattern we see in MOGAD. And here's the sobering reality of what's left behind. These are OCT scans, which give us a super high-resolution measurement of the nerve fiber layer in the retina. In the same patient, you can see that layer is severely thinned out in both eyes. That's permanent structural damage from the inflammation. It's a powerful reminder of why getting the diagnosis right, and right away, is so incredibly important.
Okay, so far we've been all about the optic nerve. But let's shift our focus a little bit. Let's move into the eye itself, because the retina can also be the main target of an autoimmune attack. These conditions are called autoimmune retinopathies.
So how on earth do you diagnose something like that? It's actually pretty clever. We can take a sample of the patient's blood serum and basically paint it onto a healthy donor retina. If the patient has antibodies against the retina, they'll stick. And in this image, you can see the patient's serum is lighting up one specific layer, the inner plexiform layer, telling us exactly where the problem is.
And this is the really cool part. This is how we prove that those antibodies are actually causing a problem. This is an electroretinogram, or ERG, from that same patient. It's like an EKG for the eye. And that B wave, which we know comes from cells in the inner retina, is way smaller than it should be. It's the smoking gun. Objective proof that the antibodies we found are causing real dysfunction.
All right, that was a lot. So let's synthesize all of this down into a practical toolkit, something you can actually use when you're on the wards or in the clinic and a patient with vision loss comes in.
Okay, here is the absolute key takeaway. If your patient with optic neuritis has any of these red flags, we're talking bilateral vision loss, a painless onset, vision that just keeps getting worse for more than 2 weeks, or it gets worse when you taper steroids, you cannot just chalk it up to typical MS. You have to escalate your workup and start actively looking for NMO and MOGAD.
So, thinking back to everything we've compared, I'll leave you with this final thought exercise. Your patient has painless, bilateral visual loss, and they're not getting better. Based on just those red flags, which diagnosis, MS, MO, or MOG, should be shooting to the top of your differential right now?
You know, the framework we've walked through today is laid out beautifully in a chapter from the Handbook of Clinical Neurology. It's a fantastic resource if you want to dig even deeper into this stuff. Thanks so much for your time.